different here is this. I'm going to apply an operation, something called a convolution here. That is applied to only a subset of neurons in the previous layers. And let me give you a demo here what this means. So typically, this type of convolutional models is applied to structured data sets. So what I mean the structured data is that your input here, there is this relationship associated with different features. So they're not random orders. So right now, everything we think about in terms of features, and we treat them as long vectors. We don't consider the orders between those features right now, right? However, but for many other data sets, for instance, the images or languages, so there is this inherent spatial relationship associated with different pixels within your image. For instance, suppose your input here is 28 by 28 images, is, with 28 pixels width and 20 pixels height here, and grayscale images and that typically is represented by a matrix. So now, in this case here, each individual pixels here, they have this spatial coherence, right? Whether they are next to each other or not. And so that's really it'd be good to have the operation here preserve the spatial relationship. The one way of doing that is to apply this convolutional operation. So in this convolution operation here, I have this something called filters here, called the weights here. You can think of the weights here. So each little blocks of the weight here is a 5 by 5 matrix, for instance. And then what I'm going to do here, I still need to do a linear combinations of the input here. But you can see the dimension here is not the same as the previous ones here. So which means you cannot apply fully connected in the linear combinations here. You have much less number of weights than the total input here. And what are we going to do here? We can apply them in a sliding window fashion. So we extract a sliding window of size the same as your weights here, and then we take the linear combinations of the input here, and then apply nonlinear activation to calculate this the output here. And then that's what we can do here. But then what are we going to do? We need to slide this window across the entire image. For each individual ones here, we take linear combinations of them, and then apply a nonlinear activation function. And that is called the active, this is treated as one output here. Well, that would be the activation of one hidden neurons. And I'm going to put them into one grid in the output here. But now, because I slide the window across the image here, I will be able to generate many hidden neurons throughout the spatial maps here. And the spatial location in the map here are preserved in the output here. Because if the two hidden neurons are next to each other, which means they are the features they extract in the input here will be next to each other as well. So by doing that, what I can do is this, I can, with the input of a spatial map here, I can generate another image here. It's also be two-dimensional map of that. So this type of operation is called a convolutional operations here. So there are several benefits of using these type of convolutional operations. First of all, so this type of features here, so W here, is applied repeatedly across different image regions of that. And this is beneficial. The reason is this, because in the image here, you might want to extract certain features. But that features here, as long as I learn this filter to extract these features here, so that filter, and I can apply different locations to extract the similar features. I don't need to have a feature only associated with one particular region. That doesn't make sense, right? That's one benefit of that. You can apply this feature extraction repeatedly once it is learned. The second benefit is this. So now you can significantly reduce the number of parameters. So in the one key limitations of this fully connected model is this. The number of parameters is actually pretty large. So because everything is fully connected here, the total number of parameters will be the number of parameters, the number of hidden neurons times the number of input neurons, and then number of hidden neurons times the number of neurons in the next layers. So it'll be polynomial degrees of complexity. So that in general is a very high number if you have many hidden neurons to that. However, if we apply this type of convolutional operations here, the number of parameters is only determined by this weight matrix here. And typically it was chosen to be relatively small, to be 5 by 5, 3 by 3, 7 by 7. So in that case, you only have smaller number of parameters here. So you can see this type of techniques can significantly reduce number of parameters here. And so this is a general one feature map, but then you don't need to stop here. You can apply a different weight matrix here to generate another feature map. So by doing that, you will be able to generate a multiple feature map as the output here. So let me show you one demo here to illustrate this point here. So this shows you how this convolution operation is done here, and in the context of the image here. So and what you can see here, what is this? This is the input here. This is the input image on the left side. Suppose this is the letter A here. I want to extract feature associated with the image letter here. So in general, this is the matrix here on the left side here. So what this convolution is do, apply this weight matrix here. We typically call it a kernel or filter. We're going to apply this kernel or filter terminology. Going to apply that repeatedly across the entire input image here, and through a sliding window project, slide across them here. And within each region, we'll calculate this linear combinations between this input image pixel values here with this weight parameter. After that, apply nonlinear activation function. I put the values on the output maps here. And because I slide across them, I will fill in the activation of the output map here. This is shown in this demo, you see. So now we go to the next rows. Once you finish that, scan across the next rows of that. So by doing that, I fill in this activation functions of that. So this is the one feature map. So now what you can do, you can apply a different weight matrix, a different kernel to generate a second feature map. So this will be apply the same process again, but now in this case here, your weight, this little moving windows here will have different weight matrices. So now you can generate two feature map. You can actually, in fact, you don't need two, you can have 3, 4. Usually you generate multiple feature maps of that. You can see that is this. So now once you have the feature map here, you can apply convolution on top of your generated hidden layer feature map here to generate another layers of the output here. And so you can apply this process recursively. And this type of the models construct this way is called a convolutional neural nets. Convolutional neural nets, and that essentially is this the building block underlying many of this existing kind of deep learning models. They are built based on this type of convolutional blocks here. All right, so that's what I want to say regarding this neural nets here. And we mainly focus on this kind of multi-layer perception models, but you can see now this models here can be generalized in other more complex models with many layers and with more complex architecture, such as convolutional neural nets here. So the key idea here is this, right? So this type of repeated applications of the feature extraction. So now you have a kind of hierarchical representations of more and more complex features. However, training these models here is using the exact same methodology we used previously. Namely, it's based on gradient descent methodology. And it's just that this so-called name of the back propagation is just kind of an efficient way of calculating this gradient with respect to the weight parameters throughout this networks of that. Of course, this is very, a lot of topics related to this neural nets here, and a modern version of that, there's a lot of tricks and techniques have been developed to improve the performance of the models, and through architecture design, through manage the complexity of the models of that. So there's a lot of newer versions of that. So in general, the neural nets model in general is not easy to train, because once you apply this nonlinear activation function repeatedly, in the end, your loss function becomes very complex. And which means that if you look at the landscape of your loss function, it has many local minimal, local saddle point, and local maximal point of that. Those type of landscape in general is very hard to for model to apply gradient descent methodology to identify the locally optimal solution. That is part of the reason why this neural net was proposed a long time ago, but had not been widely used before, is because training deep neural nets is considered challenging. So, and what changed so far? Well, nowadays we have more data to train this, to fit these more complex models, and more efficient hardware to train these models. And then we have better understanding in terms of the optimization algorithm, in terms of why, in fact, in most of the time in practice, if we apply stochastic gradient descent, it seems like we handle local optimal solution relatively well. And this seems like a big issue anymore. And so empirically speaking, and certainly demonstrate that the neural nets is nowadays becomes powerful models for many problems and turns out to doing very well. All right, so that's regarding this neural nets